Hey guys, welcome to the first video in stereochemistry. This one is just going to be an intro into chirality and what it means to be achiral. Okay, in the next few videos we'll be going through RNS configurations, some tricks on that stuff, enantiomers, diastereomers, and how some of the old reactions you guys learned in terms of alkenes can now play a role with stereochemistry, right? And so let's get started. So I drew out two molecules here, right? And so these two are going to help us learn what something means to be chiral. So what I want to do is I want to focus on the one on the left first, all right? And this is going to show us what it means to be chiral. So I have a white carbon and four substituents A, B, C, and D, and just to avoid confusion, the green C is not a carbon. I just picked from letters from the alphabet, all right? And so what does it mean to be chiral? Well, what it means to be chiral is that if I take the mirror image of a compound and try to superpose it or overlap it on the original one, they will never be able to perfectly overlap. All right, and so that's something that you should watch out for. But the problem a lot of people face is it's hard to do that. It's hard to rotate carbons either in your head or on paper, right? And model kits take a lot of time. So there are other ways to do this. And I'll show you guys tricks later on how to rotate this stuff. But some of the requirements for something to be chiral, they're pretty easy to remember. So one of the requirements is that you need to have four unique substituents. Okay. Number two, you have to be sp3 hybridized. Number three, tetrahedral. And keep in mind, this is a requirement for a chiral carbon. You'll hear the word stereocenter, and I'll introduce that in a few minutes. Okay? And so let's look at our molecule on the left. It has four unique substituents, A, B, C, and D. So we check that off. Is it sp3 hybridized? Yep. Is it tetrahedral? Also good. So we can now say that this is a chiral carbon. All right. We can also say that it is a stereocenter. Right? And so here's the thing about stereocenters. All chiral carbons are stereocenters, but not all stereocenters are chiral carbons. And what do I mean by that? We just talked about what it means to be a chiral carbon, but stereocenters are not limited essentially to talking about chirality of one atom. So in later videos and probably in a lecture, you've seen how double bonds, right? Double bonds, the carbons there are sp2 hybridized, they're not tetrahedral, and therefore they don't have four unique substituents. Yet we can talk about double bonds in terms of stereocenters because a double bond is a stereocenter in terms of the whole idea with E and Z and trans and cis. All right. So I will talk about that in a later video. But yeah, so just wanted to introduce that concept of a stereocenter really quickly. And so now let's look at what we have on the right. We have carbon. Does it have four unique substituents? Well, it has two A's, a B, and a C. So it already fails the first requirement, right? Because we have two of the A's, we can't have that. Is it sp3 hybridized? Yes. Is it tetrahedral? Yup. But is it chiral? Well, no, because it failed one of the requirements, okay? And so we can say that this carbon is not chiral, not a stereocenter. We can also say that it's achiral, right? To be achiral is the opposite of chiral. So if chirality requires, for a carbon to be chiral, it's four unique substituents. Achiral would mean it breaks something there, like it breaks one of the rules, okay? And so what you guys have seen in the lecture, the idea of taking the mirror image of something, right? Taking the mirror image and being able to superpose that on itself. So let's go through that really quickly. What that whole concept is, you've heard it in the word handedness, right? If you have a chiral carbon and you take the mirror image of that, you will not be able to superpose the mirror image onto your chiral compound, your original compound. With an achiral compound, you will be. So let's take this structure here. Take the H. Let's put an F. I'm making up a new structure for you guys, just because it's a good idea to, you know, never get like used to one structure. BR. And now let's take the mirror. And first, let's see if it's chiral or not. Does it have 4 unique substituents? Well, it has a hydrogen, a fluorine, a chlorine, and a bromine. So, yeah. sp3 hybridized? Yep. And tetrahedral? Yep. So let's take the mirror. So this is a chiral compound. So F, H, Br, and Cl. So now my job is to overlap the one on the right with the one on the left. All right. Now, you are allowed to rotate the molecule. Okay. And so, as it stands right now, if I take this and go like this, you can clearly see that the bromine, the fluorine, and the chlorine are not even close to overlapping. So what you can do, and this is where a model kit could be helpful in the beginning. Imagine your hand comes in from the top and grabs the H, and you're going to spin it around 180 degrees, right? Spin the whole entire thing around. So we're going to go and do 180 degree rotation. What's going to happen is we have this carbon, this hydrogen, okay? And now our fluorine is going to go here. The chlorine is going to go here. And the bromine would go here. Alright? So I just skipped to 180 degree rotation. Now, you'll see that if I take this and try to overlap it, the fluorine does in the hydrogen, but the bromine and chlorine don't line up. And this is going to be a common thing that whatever kind of rotation you would do, 180, 60 degrees, 120, doesn't matter, you'll never be able to get it to overlap. In a future video, I will show you guys how to do the rotations. What I'll probably do is I'll just take a model kit and I'll rotate it around a couple times to show you a bunch of different degrees, not just 180. And then I will show you after that how to do it on paper if you're a little bit stuck on that. So we can see that we can't overlap that. That means it's chiral. And so what happens if I have an achiral compound? Let's see, I have this. And now let's see, I do 2 chlorines instead. Right? It fails the first requirement of having 4 unique substituents. So, but it is tetrahedral and sp3 hybridized, but just because of that one failure, it's not chiral. And so now let's take a mirror. That was bad. All right. So now, as it stands right now, So as it stands now, if I try to take this and overlap, the chlorines don't, and the fluorine doesn't. The hydrogen and carbon does. So let's rotate this. And so I want to do the same thing. Imagine your hand comes in and grabs this H, and you're going to spin the entire molecule around 180 degrees. All right? 180 degrees. So you're going to have the H, and now we're going to have our F right there. We'll have a chlorine, and we'll have the other one here. So that's 180 degree spin, and now let's try to superpose them. Perfect overlap. Carbon and hydrogen, the fluorines, and the 2 chlorines. And so because we can overlap the mirror image on each other, onto the original, it is in fact going to be a chiral. All right. So now, like I said, I know that the rotating of the whole molecule is strange. Okay. And so in a later video, I will show you guys how to do a rotation. But there are also tricks of getting around this idea of being able to overlap them. And we can do that by just determining R and S configurations, okay? And we can determine them through that. And I'll show you guys also in a later video how we can do that. So if something in this video didn't make much sense, please feel free to email me, go to the TAs, they'd be happy to help you. If you're watching this on YouTube, feel free to comment and I can answer your question there. But I will see you guys in the next video where I'll be covering more about chirality, rotating the molecules around, and how we can do it on paper also. Alright, see you guys in the next video.